we have the binomial model part 4, I guess. Binomial model part 4. So, we are now going to discuss various nature of the stock prices itself in terms of the risk neutral probability. If you have observed, going by what we have studied in the last lecture, the nth stock price can be given like this at time n, when you know what has come out. The nth stock price can be written as conditional expectation. This is what we have discussed in the last class. You can do that, do it for Vn and whatever, everything has the same format. So, we are now going to prove that the discounted stock price, so we are going to prove that, of course, P tilde Q tilde are given, I am not repeating P tilde Q tilde, under the risk neutral probability the discounted stock price is a martingale. How do I prove? What is the meaning of martingale in this case? So, what I have to prove? So, discounted stock price. So, discounted stock price at the nth stage is this one, where R is the simple interest rate. This is nothing but the conditional expectation under the risk neutral probability. We will write it En for short. This thing I can write this as, this expression as 1 plus R. I can write this expression in short. So, when I am taking meaning, when I am writing this, I am actually meaning this, and I am actually meaning this thing. So, this random variable operates on this is the meaning, right, that is exactly what it is. Sorry, mistake in the signs. I think I will also put N here. So, this will mean that Sn is equal to this, right. N is means conditional expected at the nth stage. So, N is just to N, I am just giving the N here also, because it means at the nth stage what is happening, right. So, discounted stock price. So, this thing would be same as Sn plus 1 plus Rn plus 1. So, we will prove this fact. So, this is a very important thing, and this idea will be of primary importance even in the case of the continuous time models, because this idea would be used repeatedly in many ways in finance. This is a very fundamental idea in risk neutral pricing theory. So, these are all pricing for complete markets. For incomplete market, things are completely very different, and there are a lot of things. If suppose you want to talk about interest rate, you talk about interest rate, nothing else. So, let us see how do we go about it. There are two different proofs. I am just doing one proof, quite a direct one with what I have written. You can use formulas or properties of conditional expectation, but let me just do it directly. So, I can write this as 1 plus r to the power n 1 by 1 plus r, because this is a fixed thing, you can take it out of the conditional expectation. and this means this is nothing but 1 by r to the power n 1 by 1 plus r, because this expression is nothing but p tilde Sn plus 1 omega 1 omega 2 omega n, okay, or rather I can just write Sn plus 1, does not matter. So, omega 1 omega 2, if I want to write, I have to write omega 1 omega 2 here. I am writing everything in a functional form. So, just for brevity, Sn plus 1, basically Sn plus 1 h plus q tilde Sn plus 1 t. Actually, I should not write this. Basically, I have to be very frank with you, my actual writing should be more precise. So, if I want, I can still write it more precisely. So, let me just do it, so that you do not get confused at the end. So, conditional expectation is a random variable, it operates on this outcome at the nth stage. So, the nth stage, the sigma algebra is, the sample space is omega n, this is the sample space consisting of these sort of points, all possible n outcomes. And now, I can write this as 1 by 1 plus r to the power n 1 by 1 plus r, and writing the formula directly, p tilde Sn plus 1 omega 1 omega 2 omega n h plus q tilde Sn plus 1 omega 1 omega 2 omega n t. So, again 1 by 1 plus r to the power n into 1 by 1 plus r. So, you know this is p tilde u Sn omega 1 omega 2 omega n plus q tilde d Sn omega 1 omega 2 omega n. So, this is up down business, and then Sn is fixed, to take it outside Sn, you know. So, you have 1 by 1 plus Rn to 1 by 1 plus r into p tilde u plus q tilde d into Sn omega 1 omega 2 omega n. Okay. So, now let me compute what is p tilde u plus q tilde d. What would be this if I did? So, p tilde, if you just put the value of p tilde and q tilde, you will see what would happen is that this will become p tilde was, let me see what if I remember, 1 plus r minus d by u minus d into u plus u minus 1 minus r into u minus d into d. So, what are we getting? We are getting 1 plus r u minus u d plus u d minus 1 plus r d by u minus d. So, basically we are getting 1 plus r u minus d by u minus d. So, we are getting this to be 1 plus r. So, this is 1 plus r, the curve which cancels with this 1 plus r to give me Sn So, this occurs for omega 1, omega 2, omega and all possible combinations. So, this random variable exactly is equal to this random variable, that is exactly the type of thing that we had wanted. So, it shows that it is a martingale. Now, we talk about the portfolio process, portfolio wealth process. See, we are now talking about essentially talking about stochastic processes. If you look at the price S0, S1, S2, S3, capital Sn, that is also a finite time stochastic process. So, I am not going to tell you what is stochastic process, etc., because we have already discussed in part 1. Those who have not studied this thing in the part 1 should go back and look at the things in part 1. So, portfolio wealth process. So, what is portfolio wealth process? So, portfolio wealth process means what is happening at time delta naught, the investor buys, at time t naught he buys delta naught amount of shares of the stock. At time t1 he basically sells them, whatever money he is also getting from the money market, uses that to uses whatever he gets, and also from the money market uses that to finance. Part of the money is used to finance delta 1, and the delta 1 depends on the outcome that he has. So, delta 1 depend on the first outcome, delta 2 depends on the first two outcomes, and so forth, delta 3, delta n to delta n, sorry, delta n minus 1. So, this process is also a stochastic process. This is a stochastic process, but it is adapted to the filtration, because the delta n depends on the first n coin tosses, delta 3 depends on the first t. So, the information available up to n, time period n, is the what are the n coin tosses up to that time, and this depends on that. So, this is an adapted process, this is a process which is adapted to the filtration. So, the portfolio stochastic process is adapted, this is called the portfolio process. So, portfolio of the guy who has sold the option and is now trading in the market to hedge his exposure to risk. So, risk is essentially the whole issue. In the market there is only one issue, that is risk. All things are done just to safeguard your risk, there is nothing else. Risk is the fundamental issue. Adapted to the filtration that is generated by the coin tosses. So, what is my wealth of the portfolio at each n? So, at time t0 you invest x naught, time t1 you have x1, time t2 you have x2, time tn you have xn, time you have capital Xn. So, this is Vn and so on and so on. So, each of these random variables here that you see that make up this stochastic process, this is called the wealth process. And again this is the adapted process, it is adapted to the filtration, it depends on whatever information that you have till time small n. So, xn would depend on that, it is called the wealth process. So, that gives us something called a wealth equation. So, what is the wealth equation? That is what is the worth of the portfolio at period n. So, it is called the wealth equation. Okay. So, here the wealth equation at time n plus 1 is nothing but I have to sell what I held at time delta n, I am selling it and making this amount of money, plus I am looking at what I had invested in the money market, the xn I had in the earlier thing, of which I have bought delta n share paying Sn price and remaining I have invested in the money market, and then here n starts with 0, 1, 2 dot dot n minus 1. So, this is called my wealth equation. What sort of a process is this? This process is a martingale, that the expected value of the discounted process at time n plus 1 is same as the discounted value at Sn. So, this is a martingale. Basically, this is a no arbitrage scenario. So, martingales essentially arise in that sort of scenario. So, now we are going to show that under the risk neutral probability, so under the risk neutral probability Xn is a martingale. So, this is my wealth process, Xn is a martingale under risk neutral probability. So, these are very important information about the behavior of these processes, because what we are telling is that when you have n period models, we are generating finite time stochastic process, and here stochastic process, idea of stochastic process comes in. If you really want to know what is it, this is an Ito integral. What I have written here is an Ito integral, that is all. Ito integral in this discrete time setup. This is an Ito integral, that is all. This is actually some sort of difference between Sn plus 1, this is d of Sn basically, which we will not discuss right now, but rather we would try to prove that this is a martingale under risk neutral probabilities. So, it is not, these are not martingales under the market measure, market probabilities, never. The only market they are martingale under risk neutral probabilities, and this is a very fundamental thing, because this would allow us to compute the prices in this complete market setup where you can do perfect hedging. Otherwise, the market probability will not allow us to do anything. This is a very fundamental leap in the imagination. This is an amazingly brilliant idea to get in this risk neutral probability measures. So, martingale under risk neutral probability measure. So, our goal here finally, we are now going to show that the wealth process is a martingale, discounted wealth process. So, goal here is to really show that how can we do the computation of the option price at every step. That is okay. An option is been told that this is the selling time of the option. Somebody declares that I am going to sell an option now, and which will have an expiry time at capital N. At 0 I am selling the option, but suppose you want to buy the option at time period say 3, but your expiry is still at capital N, what would be the price you have to pay then? So, that sort of things can be answered by using the risk neutral framework. So, there are a lot of issues which are not we are not getting into. So, we are again going to show that the discounted wealth process is a martingale under risk neutral probability, and then we are going to write down the risk neutral option pricing formula, which will end our discussion. Discounted wealth process is a martingale under risk neutral probability. So, what we have to show? This is a very important pricing formula. So, we will come to that. We will show that Xn So, how do we do anything about it? Let's start looking into it. So, the proof. So, this is again a key to the pricing formula of Vn, because Vn Xn is equal to Vn, that is the fundamental fact, that at every n the worth of the portfolio, the wealth of the portfolio must match the worth of the option at n, that is it, and worth of the option at n is the price of the option at that time. So, you may buy the price of the option at any time in between time when the option is announced and time when the option is finished. You may buy at any time in between, but actually you want to know the V0 price, but at any time in between what is the worth of the option is actually the price of the option. Proof. So, let us write down. So, we will now use the wealth equation basically. So, this is written as delta n. So, whatever you have got at time n is now sold at time n plus 1 with Sn plus 1 minus 1 plus of will now be get cancelled, and you will have Xn minus delta n Sn. So, that is the amount you have invested in the money market at time n. Now, by the basic norm of, sorry, you have forgotten to write expectation. So, by basic facts about expectation or conditional expectation, because they are linear, so you can write that so because I had used P tilde Q tilde, I am giving this tilde sign to say that this is under risk neutral measure, risk neutral probability measure. Now, at time n, Xn is completely known, Sn is completely known. At time n, if I am starting at time n, I know what is the price at time n. So, I know what is the portfolio worth at time n, right. So, whatever is known has to be taken out, right. At time n, delta n is also known. If I am, because this is things are done at time n plus 1, but at time n, right, delta n is also known. I know how much I have to buy now, right. So, delta n, I am taking out what is known. You see how things are beautifully coming in. Now, here also it is like taking out what is known, this into the variable 1, a constant random variable, which will give you 1. So, basically this is at n, this is now constant basically, and this is completely known, this is just a constant. So, the expectation of that constant is, so this is same as taking out what is known. Now, what does this tell us? We have already known that the price process, the discounted price process is a martingale under risk neutral probability. This will give me delta n Sn by 1 plus r to the power n minus Xn minus delta n Sn 1 by r to the power n. This I have used the fact that this is the martingale, the price process is a martingale. So, what I have now got is E tilde Xn plus 1 1 plus r to the power n plus 1 is equal to delta n Sn by 1 plus r to the power n minus xn minus delta n Sn by 1 plus r to the power n. So, what I am getting? 1 plus r to the power n delta n Sn minus xn plus delta n Sn. So, this is giving me xn into 1 plus r to the power n. This is exactly what I had wanted. Now, this has a magical conclusion, because at every stage n, for the risk to be completely hedged or perfectly hedged, the worth of the portfolio, the value, wealth of the portfolio must match the worth of the option, which means now from here I can write that Vn by 1 plus r to the power n is En Vn plus 1 by r to the power n plus 1. So, basically then from here I will get Vn, if I take this one and bring this out, is 1 by 1 plus r, which way we had been studying all along. So, this is called the risk neutral pricing formula. It is called the risk neutral pricing formula for an option. So, if you put n equal to 0, it is V0, V1, E0, V1 means nothing but the expectation, E0 is what, expectation of V1. So, again V1 would be bought again. So, you have to go back recursively. This whole process, when we write this formula in continuous time, would actually generate the Black-Scholes model using probability theory. That is one of the fundamental things that we had been trying to tell through this discussion. So, here in this discrete setup, we have got finally into a framework by which we can now move into the continuous setup. You see, once you have got an idea about the discrete setup, a lot of things in the continuous setup would look similar. You will say, okay, of course, there your discounting price would be something like this. This would be a discounting parameter instead of 1 plus r and all those things. So, except those things, the continuous version, the limit versions of them, everything else would look like similar. So, learning the discrete time part is absolutely of fundamental importance. People think, oh, forget the discrete time, just do the continuous time. That is absolutely a wrong thing to do. So, next week, the last session, we will use things which we have already spoken in the part 1. And so, those who have known, those who have done the part 1, it is fine. Those who haven't done, please have a look at them. Thank you.